Hi, I'm Agathe. I'm a PhD candidate at TU Delft, and I'm happy to present our work on developers' practices towards debugging computer vision models. Computer vision models might suffer from various failures in their outputs. This might cause different types of harms. For instance, this famous example of a Tesla car that slowed down on the road because it confused the yellow traffic light with the orange sun, well, could have caused quite some accidents. And we have other examples, such as this Google Vision API that confused a hand holding a thermometer with a gun, which is an error that can also be offensive. We have all these different kinds of failures that might lead to harms on one side, but on the other side, surprisingly, the research literature on machine learning, computer vision debugging, explainability, fairness is also increasing. So we could, in theory, expect the number of accidents to actually increase, but that's not the case. And so in this work, we wanted to understand how developers actually debug their models for the failures and the potential harms, and whether the challenges they face are supported or not by the literature. To do so, first, we needed to understand what might be the technical causes of the failures. And we found three types of bugs that might cause these failures. Of course, the configuration of the machine learning model, so the training data set, the training hyperparameters, model architecture, parameters, etc., might be problematic, and that might lead to, the failures. Another type of bug is when the configuration that is intended is not correctly translated into an implementation, of course. And finally, the script to train the model might simply not run, and that might also, of course, lead to errors. We wanted to see whether the research is supporting all bugs or not, and whether developers might then use these bugs. And so when we looked into research, we found that there is a lot of research for the first two bugs. You can think of machine learning testing, robustness, explainability, or even HCI works that propose user interfaces, for instance, to warn developers about potential errors. But we couldn't find any literature that looked into the developers' practices, whether they use the tools, whether the tools support them correctly, etc. And so that's what we settled to study in our work. There was already quite a lot of work in software debugging, software engineering literature for the third type of bugs. So what kind of approach did we take? We took a three-step approach. First, we conducted reviews of the literature to understand what developers might want to look into. What are the goals, for instance, that they might want to have when debugging their models? For instance, we found that there are different types of failures, not only for the outputs and their correctness, fairness, etc., but also for the model process, for instance, the training process, whether it's privacy infringing, etc. And so we wanted to know which are the goals that the developers actually take in practice. Then we looked also in terms of processes. Software debugging tells us already quite a lot about software debugging workflows, going from hypothesis formulation to hypothesis correction or solution application. And so we wanted to investigate whether developers follow this same workflow or not. And then we also found many other tools that might be proposed in research that we wanted to investigate whether they can be useful or not, especially, for instance, different types of explainability methods that might or not be used in practice by developers. So once we had this information about the existing literature, we proceeded to perform interviews with 18 machine learning developers who had different background with computer vision, different experience. And then we analyzed the interviews based on the literature to identify whether they could be supported by proposed methods, or whether they might face challenges that are different. During the interviews, what we did is to present them with a design brief. In this design brief, we were asking them to debug a scene classification model, and we were presenting them different images reflecting the predictions of this scene classification model. We especially presented different types of failures and bugs implicitly when we were presenting the design brief. For instance, we showed the confusion matrix with different accuracy per classes. We also hinted at the distribution shift by showing training images, as you can see on the screen, that were only high-resolution images from lectures rooms, which might not be the case of the images the model would see in deployment. And we also hinted at various spurious correlations, for instance. For instance, here you can see images of bedrooms correctly classified as bedrooms, which already have a bed. But then an image of a living room incorrectly classified as bedroom because probably something which looks like a bed is there. And so then the developers could think that there was a problem with the model features that were learned. Maybe features were incomplete, leading to these errors. And let's take a look at the results of our interviews and analysis. So first, in terms of goals, interestingly, the developers would not all look into the same goals. Of course, they all look at model correctness, but then other goals such as looking into the distribution shift or robustness to natural perturbations of features was more disparate. For instance, this developer mentioned that they focus first on the errors, and later on, at the end, they might look into whether the model understood the classes, so the model features. We also found that not all practitioners are aware or investigate all types of bugs. So for instance, this developer here said that they would look either into the data or the system parameters, but not both. The interviews also enabled us to refine the categories of bugs that exist. Literature always talks about structural bugs, so related to the model architecture, or training bugs without distinction, but we found different types of training bugs that you can see here. Then we looked into when the developers decide that they are satisfied. And here we also found a lot of disagreement and variability. For instance, one practitioner said the business owners should say when the metric they choose is good enough. Others mentioned that they go for as much accuracy as possible by doing various experiments. And we also found ambiguity in terms of metric and usage of metrics to define whether something is satisfactory. For instance, a developer was saying that they use certain error metrics, accuracy, for instance, but if they could understand certain errors, then they wouldn't consider that as an error. So then the metric wouldn't really be meaningful anymore. In terms of workflow processes, we found that oftentimes the process is much simpler than for software debugging. So in terms of structural bugs around the model architectures, typically they don't really formulate a hypothesis and test them, but they simply try different architectures, as this developer mentioned. In terms of dataset bugs, here we found that there was more exploration, looking at different images to formulate different hypotheses. For instance, in terms of features the model might or not have learned, in terms of data samples that might be problematic, etc. And then in terms of testing hypotheses, some developers would actually test hypotheses by transforming images and looking at what would be the resulting prediction of the model, which was different for the structural bugs. So already these results bear a lot of implications. For instance, we found that in theory, the workflows should be diverse. And well, they depend on the bugs that are targeted, the type of failures that are targeted. We also found that in terms of practices, developers are not all looking at the same practices. Sometimes they forget certain failures and bugs. They are not all confident in using new tools, etc. So this gives a lot of insights for research, future research. For instance, the development of tools to support certain steps of the debugging workflow, such as hypothesis testing, but also the need for more tools to support or to guide practitioners to look into the different failures and bugs, and different ways to educate them around those topics. And finally, we zoomed in on explainability needs because, well, that's quite a lot researched. We found that practitioners use only one type of explanation, the silency maps, but sometimes they wished for other explanations. And they used explanations for different purposes, not always to identify bugs, but also sometimes just to verify whether the model seemed correct overall. So in the paper, we propose a list of research questions or questions the developers ask themselves when developing models, and these can lead to identify new research questions. So for instance, we have questions about the data that the model was trained on that are not necessarily yet easily answerable with existing tools developers have, and for which we could then develop more tools. We also have questions about how to judge whether a model is satisfactory based on its features, and this lead to research questions around supporting practitioners with expert knowledge that is needed to judge whether a feature is okay or not. So that's all about the implications that we had, and I'm happy to answer any question